Preparing for a SoC Design Engineer interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you approach the architecture of a new society from requirements to implementation? At the architectural level, I decompose requirements into compute, memory, interconnect, power, performance, and safety targets. I define interfaces, clock and reset domains, then choose IP versus custom logic. I evaluate bandwidth with traffic models, estimate area and latency, and identify bottlenecks early. Finally, I make the design configurable where reuse matters, while freezing critical paths and validating assumptions through architecture reviews and executable models. While answering, cover performance, power, area, and cost targets, partitioning hardware and software, IP reuse, memory and interconnect choices, clock and reset planning, interfaces, and early modeling or feasibility analysis. Question 2. What is the difference between blocking and non-blocking assignments in SystemVerilog, and when would you use each? Blocking assignments execute immediately and are appropriate for combinational calculations, where statement order represents data flow. Non-blocking assignments update simultaneously at the end of the time step, so I use them for clocked state elements. For example, an always FF block with non-blocking assignments models flip-flops correctly, while always COM uses blocking assignments for intermediate signals. I also avoid multiple procedural drivers and rely on linting to catch ambiguous intent. Make sure to explain simulation scheduling, combinational versus sequential logic, race avoidance, inferred hardware behavior, always COM and always FF usage, and why mixing assignment types carelessly can create simulation synthesis mismatches. Question 3. How do you safely transfer signals between asynchronous clock domains? The solution depends on the signal type. For a single-bit level, I use a 2-flop synchronizer in the destination domain, accepting added latency and residual metastability risk. For pulses, I prefer a toggle or request acknowledge handshake so events are not missed. For streams, I use an asynchronous FIFO with gray-coded read and write pointers. I constrain and review every CDC path, then run structural CDC analysis before sign-off. In your answer, distinguish single-bit controls from multi-bit data. Discuss 2-flop synchronizers, pulse and toggle schemes, asynchronous FIFOs, gray-coded pointers, metastability, latency, and CDC verification tools. Question 4. What causes metastability, and how do you reduce its impact in a digital design? Metastability occurs when a flip-flop samples an input near its setup or hold window, leaving the output temporarily unresolved. I reduce its system impact by using dedicated synchronizer chains, increasing resolution time, placing synchronizer flops physically close, and avoiding direct use of asynchronous signals in logic. MTBF improves with more resolution time and lower event frequency. I never treat synchronization as a substitute for a correct handshake or protocol. Be sure to mention setup and hold violations, metastable resolution time, synchronizer mean time between failures, clock frequency, destination aperture, physical placement, and why synchronizers do not eliminate metastability completely. Question 5. How would you design a robust reset strategy for a complex society? I separate reset sources and domains, defining which blocks require power on reset, warm reset, or software-controlled reset. Asynchronous assertion can provide immediate protection, but I synchronize deassertion independently in each clock domain to avoid recovery and removal violations. I specify reset values and ordering for every stateful block, including retained logic. Verification must test reset during traffic, clock changes, power transitions, and partial subsystem shutdowns. Focus on power on versus software reset, synchronous and asynchronous assertion or deassertion, reset domains, sequencing, retention, reset-release synchronization, X-propagation, and verification of reset behavior during active transactions. Question 6. How do you choose between an AXI, AHB, APB, or custom interconnect for an society subsystem? I select the protocol from traffic requirements. AXI suits high bandwidth memory and accelerator paths because it supports bursts, separate channels, and outstanding transactions. APB is efficient for low-speed control registers, while the AHB fits simpler shared memory subsystems. I examine latency, ordering, arbitration, clock crossings, and bridge overhead before deciding. A custom link is justified only when standard protocols create measurable cost or performance problems. Discuss bandwidth, latency, burst support, outstanding transactions, ordering, register access, area, power, bridge requirements, arbitration, protocol compliance, and matching the bus to the workload rather than choosing by familiarity. Question 7. How would you investigate and fix an society timing violation? I first classify the violation as setup, hold, or a constraint issue. Then inspect the full timing path, launch and capture clocks, exceptions, and cell delays. For setup, I may reduce logic depth, pipeline the data path, improve placement, or optimize high fan-out control. For hold, I add delay carefully or adjust clock balance. I rerun timing across all corners and modes, checking area, power, and functional equivalence after each change. In your answer, explain setup and hold analysis, worst negative slack, path reports, constraints, logic depth, fan-out, placement, buffering, pipelining, useful skew, and checking that fixes do not damage power or functional correctness. Question 8. What techniques would you use to optimize in society for power, performance, and area simultaneously? I optimize PPA hierarchically, starting with architecture because an algorithm or memory change often beats local RTL tuning. I reduce switching through clock gating and operand isolation, use power gating where state retention permits, and select voltage, frequency, pipeline depth, and memory sizes from workload data. I track area, timing, leakage, and dynamic power together. Every optimization needs representative simulation or emulation evidence, not just synthesis estimates. Cover the PPA trade-off, architectural optimization before RTL tweaks, voltage and frequency scaling, clock gating, power gating, operand isolation, memory choices, pipeline depth, activity estimates, and measuring improvements with realistic workloads. Question 9. How do you design and verify a low-power society using power domains? I partition domains according to activity, voltage needs, and independent shutdown opportunities. Signals crossing from an off domain require isolation, while voltage differences require level shifters. Selected state uses retention flops. I describe intent with UPF, define legal power states, and include always-on control logic for isolation and wake-up. Verification must prove correct sequencing, retained state behavior, isolation values, and recovery after interrupted or repeated power transitions. Mention power domain partitioning, isolation cells, level shifters, retention registers, power state sequencing, UPF or CPF, always-on logic, illegal transitions, and verification across voltage, power, reset, and wake-up scenarios. Question 10. What is the role of caches and coherency in a multicore society? Caches exploit temporal and spatial locality, reducing average memory latency and interconnect traffic. In a multicore society, coherency ensures that cached copies reflect a consistent ownership protocol, while consistency defines the ordering visible to software. I would evaluate snooping for smaller systems and directory schemes for scalability. Design decisions include write-back policy, sharing patterns, atomic support, and memory barriers, because coherency traffic can dominate performance and power. Be sure to explain locality, cache levels, write policies, coherency versus consistency, snooping or directory protocols, invalidation and update behavior, atomic operations, memory ordering, and traffic or power implications. Question 11. How would you design a DMA engine for high-throughput data movement? I start with the transfer model, endpoints, burst sizes, alignment, maximum outstanding requests, and required throughput. A descriptor-based scatter-gather engine supports large fragmented buffers without processor intervention. I add backpressure, programmable priorities, boundary checks, and clear error reporting. For cacheable memory, I define coherency or explicit flush and invalidate rules. Finally, I benchmark sustained bandwidth, small transfer latency, arbitration fairness, and interrupt overhead under competing traffic. Discuss descriptors, scatter-gather operation, burst sizing, alignment, outstanding requests, backpressure, arbitration, address translation, cache coherency, interrupt moderation, error handling, and measurable throughput or latency goals. Question 12. What is the difference between simulation, emulation, FPGA prototyping, and formal verification? Simulation provides excellent signal visibility and flexible checking but is relatively slow. Emulation and FPGA prototypes execute much faster, making them useful for long software workloads, though debugging and timing fidelity are more constrained. Formal verification explores all legal behaviors within a modeled scope and can prove properties such as protocol safety. I combine these methods: simulation for detailed scenarios, formal for exhaustive local guarantees, and emulation for system-level software validation. Explain speed, visibility, capacity, and proof guarantees. Identify suitable use cases for each method. Discuss constraints, abstraction, coverage, and why a verification plan should combine complementary techniques. Question 13. How would you build a verification plan for an society subsystem? I convert the specification into features, risks, interfaces, and measurable coverage goals. The environment combines directed tests for architectural requirements, constrained random traffic for interactions, assertions for protocol invariants, and a reference model or scoreboard for data correctness. I include reset, backpressure, overflow, illegal accesses, clock crossings, and error injection. Coverage closure requires reviewing exclusions and unhit scenarios, not merely reaching a numerical percentage. Cover specification-derived features, interfaces, assertions, constrained random stimulus, functional and code coverage, reference models, scoreboards, error injection, corner cases, regression strategy, and coverage closure with measurable exit criteria. Question 14. Which SystemVerilog assertions would you write for a valid ready interface? For a ready valid interface, a transfer occurs when both signals are high on a clock edge. I assert that valid remains high and payload remains stable while valid is high and ready is low. I also check reset values, response ordering, and any specified maximum wait time. For example, a property can use to require payload stability on the next cycle. I add cover properties for back-to-back transfers and sustained stalls. Mention the transfer condition, stability while stalled, no illegal response, bounded latency where applicable, reset behavior, clocking assumptions, implication operators, and combining assertions with coverage for meaningful protocol verification. Question 15. How do synthesis and RTL coding style affect the hardware that is generated? Synthesis interprets RTL as hardware, so coding style directly influences the inferred structure. An incomplete combinational assignment can create a latch, while a variable indexed array may infer RAM or a large multiplexer depending on technology and constraints. I use always COM and always FF, complete assignments, explicit widths, and vendor guidance for memories. Then I inspect inferred hardware, area, timing, and power reports to confirm the implementation matches intent. In your answer, discuss inferred registers, latches, multiplexers, RAMs, and clock enables. Explain coding constructs that synthesize poorly. compare simulation intent with mapped hardware, and emphasize reviewing reports rather than trusting RTL appearance. Question 16. What are scan chains and other DFT techniques, and why are they important? DFT improves controllability and observability of internal circuitry after fabrication. Scan chains replace or connect flip-flops into shift paths, allowing external patterns to set and observe state for stuck-at and transition faults. Compression reduces tester data and time, while MBIST targets embedded memories. Boundary scan supports board-level testing. I plan test clocks, modes, resets, and power limits early, then verify that DFT logic does not compromise functional timing. Be sure to cover controllability, observability, scan insertion, stuck-at and transition faults, compression, test points, memory BIST, logic BIST, boundary scan, test modes, and the impact on area, timing, and power. Question 17. How would you debug an intermittent data corruption bug in silicon? I would first characterize frequency, workload, temperature, voltage, revision, and exact failure signatures. I would use on-chip trace, error counters, ECC syndromes, and software logs to narrow the failing boundary. Then I would compare silicon evidence with simulation and formal properties, focusing on CDC, reset sequencing, arbitration, and protocol ordering. Controlled changes, such as reducing frequency or disabling a feature, help isolate causes. I preserve every failing trace for regression. Discuss reproducing conditions, logging and trace, observability, boundary isolation, CDC and reset review, ECC or parity evidence, waveform correlation, assertions, controlled experiments, and distinguishing design defects from environmental or software causes. Question 18. How do you handle clock gating and multiple clock frequencies in a society? I use library integrated clock gating cells rather than casually gating clocks with combinational logic, ensuring enables change safely relative to the clock. For multiple frequencies, I document synchronous relationships, generated clocks, PLL behavior, and asynchronous boundaries. Frequency changes require controlled sequencing and confirmation that consumers tolerate the transition. Timing constraints must model every mode, while verification checks enable glitches, wake-up latency, lost transactions, and correct operation when clocks stop. Focus on glitch-free integrated clock gating cells, enable timing, clock domain relationships, PLLs and dividers, generated clock constraints, frequency changes, CDC boundaries, wake-up latency, and verification of gated clock behavior. Question 19. How would you design an interrupt controller for a multicore society? I define source semantics first, edge or level, pulse width, clear behavior, priority, and whether events may be coalesced. The controller synchronizes asynchronous sources, latches pending state, applies masks and priorities, and routes interrupts according to processor affinity. For level interrupts, acknowledgement must not lose an asserted condition. For edge events, reliable capture is essential. I include nesting and end of interrupt handling, plus software visible status for diagnosis. Cover interrupt sources, masking, priority, edge versus level triggering, pending and active state, routing, affinity, synchronization, nesting, acknowledgement, end of interrupt behavior, and robustness against lost or repeated interrupts. Question 20. What checks are required before signing off in society design? Before sign-off, I require passing functional regressions, assertions, lint, CDC and reset domain checks, formal equivalence, and agreed coverage targets. I review synthesis, multi-mode multi-corner timing, power, IR drop assumptions, DFT coverage, and gate-level behavior where necessary. Physical sign-off includes design rule and layout versus schematic checks. Low power intent, security properties, boot flows, and configuration combinations also need validation. Every waiver must be justified, reviewed, and traceable. Mention RTL and gate level verification, lint, CDC and RDC, synthesis, STA across corners, power analysis, formal equivalence, DFT coverage, physical checks, low power validation, security requirements, and documented waiver review. If you are still with us, congratulations! You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.